In today's video, we would like to discuss about the properties of a continuous function f defined over a closed and bounded interval if. So we assume that f maps I to R is continuous and this interval I is closed and bounded. So for all continuous function defined on a closed and bounded interval, we intend to prove that f attains its bounds. F attains its bounds. So first of all, let us make it clear that since this interval is closed and bounded, so all the values of x lying within this interval is bounded, and we have, since fx is continuous, it must be bounded. Okay, and we have famous Bolzano-Weierstrass theorem, which states that this is a very crucial theorem. I'd like to highlight the power of this theorem and how much it is being used to unravel the different properties of continuous function over a real line. So since fx is continuous, it must be bounded, because whenever fx is continuous, we have a convergent sequence, any convergent sequence in terms of x, xn, fxn converges. And we tend to prove that f attains its bounds. It means that since x is bounded, it have a supremum or least upper bound and a minimum, infimum rather, which is greatest lower bound. Okay, we would like to show if this S star and S, they are the LUB and GLB of fx. Fx is also bounded. We have some x star for which this is this, and we have to show this using this Bolzano-Weierstrass theorem. Okay, so the framework is that f is continuous function defined on a closed and bounded interval. Then we are to show that f attains its bounds within this interval. That means there are values x star such that f of x star is equal to s star. Okay, so to prove this, what is S star? S star is least upper bound of fi, where I is this interval. Fairly reasonable. We assume that S star is the least upper bound of fi. So since this is the least upper bound, we have S star minus 1 upon n. This will not be the upper bound of this Fi. Isn't it so? This is the definition of least upper bound. Since S star is least to be the upper bound, so S star minus 1 by n for all natural number n, this is a positive quantity and this is less than S star. So we have this, and this must be, we put a equal to sign here. This is fairly reasonable and conceivable, isn't it so? So this xn is chosen from this interval, and for each n, for any n rather, whatever be the n, we have this true, and for this set of values we have xn, for which fxn is less or equal to S star. So this is a very crucial relation. So we have a sequence xn, isn't it so, for which this is true? We have a sequence xn for which this is true. And since any sequence in this interval, this xn, each xn is member of AB or I, whatever is, and I is bounded, closed and bounded. So xn converges, we have a subsequence xnk which converges to, say, limit x star, and that must be E9. This is Bolzano-Weierstrass theorem, isn't it so? This is bounded, this is any sequence, it has a subsequence which converges to a limit, which limit is a member of this. And since f is continuous, for every sequence xnk converging to fx star, we have another sequence fxnk which converges to fx star, isn't it so? This is also granted since f is continuous. Okay, so we have, apart from this we have also this. And we can at best choose this nk to be greater than each n. And we have from Squich theorem that this A star is nothing but f of x star. From Squich theorem we can easily write this. Why? Because if we have xn prime and xn double prime such that, and if we have limit xn equal to limit xn double prime equal to L, then Squich theorem says that limit xn prime converges to the same limit. So we have A star equal to fx star, and that means f attains its bound because x star is in I. So this is a very, very crucial theorem which states that if f is a continuous function from any closed and bounded interval, then f maps I to R is continuous. Then f attains its bound. This is very important, as we have established that f is bounded whenever f is continuous and I is closed and bounded. F is bounded whenever I is closed and bounded. And f attains its bounds in this interval only. We have another very important theorem which uses nested interval property to establish that if f maps any closed and bounded interval real valued function such that if a into fb are of opposite sign, that means their product is negative. This is very vital. If fa is positive, then fb must be negative. Either or vice versa, if fa is negative, then fb must be positive. Okay, if we can draw a figure, this is x and this is fx, and we have a here and we have b here. Obviously b is greater than a, so if a is positive, if fa is positive, then fb will be negative, and vice versa, if fa is negative, then fb will be positive. And since f is continuous, then there must be a point C within a B such that fc is equal to 0. Okay? From the figure, it's quite obvious, and it can be shown algebraically simply by bisection theorem with the property of nested interval theorem. You all know the technique which I will try to explain in a nutshell. Let us suppose that this is A and this is B. If A is positive and FB is negative, there is no loss in general. If F is negative, we assume FB is positive. We take the middle point, A plus B by 2. Okay? A plus B by 2. Since this is origin, this measures A, this measures B, and obviously this measures A plus B by 2. So the length of this interval is B minus A, and it is divided in these two subparts, each having length B minus A by 2. We can easily find that A plus B by 2 minus A is B minus A by 2, and B minus A plus B by 2 is also B minus A by 2. And then we check whether f of A plus B by 2 is positive or negative. We have assumed that f A is positive and f B is negative. We have assumed this. Now if this is positive, we take this interval, and if this is negative, this point A plus B by 2, then you take this interval, because obviously the root lies between them, and we subdivide it, again take the middle point, and the length will be B minus A by 2 square, obviously, and we keep on dividing just by checking this. And we have a sequence of nested intervals. Obviously, if we term this to be I and then this 2 to be I1 and the subsequent to be I2 and then I3 so on, then Ik will have length b minus a by 2 to the power k, and we have the nested interval where I contains I1, I1 contains I2 and so on, Ik plus 1 and so on. Okay. And after a sufficient number of iteration, when k or n becomes very large, then the length of this subinterval tends to 0. That means it converges to a specific point C for which fc is equal to 0. It's not positive or negative, but fc is 0. That means the continuous function crosses this line. So this is the concept. I would like to mention after this discussion that with the help of these two, we can say that if we have a function again which is continuous and defined on a closed and bounded interval I, then we can claim that there is a value C within A and B such that there exists a value C in the open interval A. F is continuous. This is the prerequisite. For any real valued continuous function which is defined on a closed and bounded interval, we have a point in the open interval. We leave these two endpoints. There exists a point fc such that fc equal to k, where this k lies between fb and fa. It may as well be like this. Sorry. Okay. So this is the corollary of the first theorem which we established using Bolzano-Weierstrass theorem, that f attains its bounds. And then we have shown that there is the nested interval theorem or the location of root theorem. Using nested interval theorem rather, we have the location of root theorem, which states that if fa and fb at these two endpoints are negative, product of them, that means they change a sign. If fa is positive, then fb is negative, and vice versa. Using these two, we can establish that for all continuous function defined on a closed and bounded interval, there exists some c in AB for which fc equal to k, where k is any intermediate value between A and B. This is very crucial. We assume this, that means fa is increasing, isn't it so? Fa is the lower bound of fi and fb is the upper bound of fi. We assume this. There is no loss of generality. In other way, we can assume that this is decreasing. And then we construct gx equal to fx minus k. And we can obviously see that this is, since fa is less than k, so this will be negative, and this will be positive since fb is greater than q, and if we assume this, it will be vice versa. And since GA and GB changes sign, that means they are of opposite sign, we have GC equal to K. Sorry, GC equal to 0. That means FC equal to K. GC equal to 0 means FC equal to K, which is our motto. So, we have established that for any continuous function defined in a closed and bounded interval, this is very important, we have f taking all the values in between fa and fe, since f is continuous. It actually establishes the smoothness of f. F being continuous, it is smooth and it attains its bounds, every value in between f and fb, and that helps us to expand fx as a Taylor series expansion. Which is where theta is this. This follows from the mean value theorem This is the mean value theorem. Rolle's theorem actually. We have another mean value theorem, Cauchy's mean value theorem. Sometimes it is called Lagrange's mean value theorem also. And we have for f mapping I to R, real valued continuous function for which we have if A equal to FB, for which we have if A equal to FB, where I is the closed and bounded interval AB, F is continuous, and the endpoints are equal. If we assume that F is a derivable in the open interval AB, we don't require this function f to be derivable at a and b. It may not be derivable in the endpoints, may not be smooth, but within that interval it is smooth. Smooth means we can draw a tangent, that means it is derivable. And if a and b are equal, then we have a point C in this open interval, there exists, for which f prime C is equal to 0. This is actually Rolle's theorem. This also follows from the concept of attaining the local minima or local extrema. How? Let us draw a picture for it. Let us give a pictorial expression. The algebraic proof is fairly simple. Okay, so this is A and this is B. So this is f of A and this is f of B. Obviously we have assumed that both A and B are positive. We can as well assume that both A and B are negative. Obviously it is given that fa and fb are equal. Okay, so if fa and fb are equal and if fx is a constant function, then we have nothing to prove, isn't it so? This is a straight line, y equal to some constant, and we have f prime x equal to 0 for all x in AB. Let us write it open interval. And it is not, and if it is not so, it must be either increasing or decreasing. It may as well be like this, it may as well be like this. A part decreasing then increasing, whatever be it. We can make this interval smooth by dividing it into parts. And from here we see that there is some point at which the tangent becomes parallel to x-axis. That means its gradient is 0. Okay, it can easily be established